Modern AI training on ROXA V2 fabrics requires a flawless, frictionless pipeline of exabyte-level data to function efficiently. Traditional deep packet inspection, or DPI, acts as a toll booth for this traffic. Every packet is stopped, opened, and checked against a database of known threats. At a small scale, this works, but forcing payload analysis on the vast oceans of data required for large language models introduces massive compute overhead. It physically throttles the network. High-performance enterprise databases and AI node synchronization require deterministic, near-wire speed performance. The compute-intensive nature of DPI disrupts this, introducing latency that chokes the very workloads it is meant to protect. Scaling up legacy defenses by racking more DPI firewalls fails to fix the architectural bottleneck. It simply multiplies the number of checkpoints the data has to survive. Data centers are left choosing between achieving high-performance AI compute or maintaining secure infrastructure. Beyond latency, signature-based defenses rely entirely on databases of previously identified threats. When state-sponsored actors deploy novel, zero-day lateral movements, a signature-matching firewall simply lets them pass. Threat actors obscure their code inside heavily encrypted payloads. By the time DPI uncovers the intent, the exploit is already spreading. Inspecting those payloads presents a massive compliance liability. Opening data packets violates strict zero-trust privacy mandates across defense, finance, and healthcare sectors. The Predictive Tensor Control Plane, or PTCP, solves this by abandoning payload inspection entirely. Rather than looking at what data is moving, PTCP evaluates how the network behaves structurally. It tracks the physical flow and routing patterns between nodes. Operating completely payload-blind eliminates both the privacy liability and the latency bottleneck, satisfying the strict requirements of hyperscale zero-trust compliance. To achieve this, PTCP pulls standard fleet telemetry natively from across bare metal clusters and virtual private clouds. Instead of reading this as a flat list of IP logs, the engine converts traffic flows into a dynamic geometric topology. Standard enterprise traffic establishes a distinct baseline, maintaining a stable structural shape. Overlays calculate a graph curvature estimator, continuously mapping network connections in real time. Because this relies entirely on routing metadata rather than decrypting payloads, the calculation requires virtually zero compute overhead. Invisible network behavior is translated into a highly precise, geometrically measurable surface. Consider a coordinated hacking attempt, or a ransomware strain actively trying to spread laterally across a VPC. The exploit's payload might be perfectly disguised. However, forcing lateral connections to spread the infection causes a violent warping in the network's geometry. This structural defect is instantly quantified as the D-topo score, mathematically proving a disruption in the topology. The system distinguishes between massive, benign data surges and malicious activity because high volume does not deform the established routing architecture. Unauthorized lateral spreading does. A zero-day exploit can hide its code, but it cannot mask the structural deformation required to move laterally. By identifying the presence of a threat through its geometric wake, PTCP enables the detection of lateral movement even when the exploit has never been seen before. This mathematical theory doesn't just live in the cloud, it executes directly at the hardware layer within the data center's core. The PTCP engine deploys as an eBPF-powered Docker container running exactly on the Switch Linux kernel, integrating with systems like Sonic or NVIDIA Bluefield DPUs. The microsecond a D-topo score registers a severe gradient magnitude, the trigger mechanism fires. This initiates a safe policy envelope projection. The switch kernel drops the red malicious packets directly at the wire level, while green adjacent traffic flows without interruption. The compromised node is instantly quarantined. This isolation process occurs autonomously at the kernel layer, requiring zero human intervention. Operating at the eBPF layer guarantees zero blast radius containment and ensures that adjacent cloud workloads experience zero added latency. This dashboard outlines the strategic reality of deploying PTCP across a Fortune 500 footprint, mapping immediate advantages against necessary operational trade-offs. Because PTCP is strictly payload-blind, it cannot see inside individual data streams. Highly localized application layer logic flaws, like a single SQL injection, will bypass the topological filter. Security operations centers must adapt. SOC teams have to transition from investigating explicit signature-based alerts to monitoring topological probability-based threat models. Rigorous baselining is mandatory. Massive, unplanned data migrations or erratic but benign structural changes must be accurately mapped to prevent a false topological quarantine. Deploying PTCP requires a highly calibrated operational model to balance precision and performance. To ease this transition, the software deploys natively using standard Kubernetes orchestration or Ansible playbooks. CISOs are advised to initiate integration through a 30-day shadow mode proof of concept. During shadow mode, the system passively ingests eBPF telemetry and computes D-topo curvature scoring. It maps anomalies and tracks gradients without actuating any active quarantine policies. This dual-axis graph compares standard SIEM threat alerts on the bottom against predictive D-topo anomaly spikes on the top. It provides a direct side-by-side validation, showing how the mathematical model registers the threat earlier than traditional tooling. This 30-day window delivers the empirical proof organizations need to confidently transition away from legacy defenses and toward a fully autonomous, topology-native defense posture.